Module 7, Lecture A, Greedy Strategy. At the end of this lecture, you will be able to describe the greedy algorithm design paradigm and its key assumptions, implement classic greedy algorithms in Python for problems such as interval scheduling or coin change, and evaluate whether a greedy approach is likely to be correct for a given problem. Core greedy principles. Greedy choice insight. A greedy choice means always taking the best-looking option at each step of a problem, based on a clear measure of what is most desirable, and never going back to change earlier decisions. Instead of planning all possibilities in advance, you focus only on the current situation and lock in the option with the greatest immediate benefit. This contrasts with exhaustive or backtracking methods that explore many combinations and may revise past choices. The key idea is that for certain problems, this locally optimal, short-sighted strategy can still produce a globally optimal overall solution. A greedy algorithm relies on a greedy criterion, which is a rule for deciding what looks best at each step. Choosing this rule is often the hardest part of designing such an algorithm. For example, to reduce waiting time for a train, you might always board the first one that arrives, while for finishing tasks before deadlines, you might always do the task with the earliest deadline first. In each case, the rule must match the structure of the problem so that every local choice helps move you toward an overall optimal solution. Greedy strategies make decisions based only on what seems best at each step, but this does not always lead to the best overall outcome. For instance, picking the least congested road at every turn might actually make your trip longer, while choosing the appointment that finishes earliest can help you fit more into your schedule. The crucial idea is to know when a locally optimal choice supports the overall goal. Understanding this helps you judge when a greedy approach will produce an optimal solution and when it is likely to fail. Building optimal solutions. A greedy algorithm builds an optimal solution step by step by always choosing the best available option at each stage. Once a choice is made, it is never changed, and the algorithm does not backtrack or reconsider earlier decisions. Over time, these local best choices combine to form a complete solution. For example, in meeting scheduling, you repeatedly add the earliest finishing meeting that still fits without revisiting past selections. Under the right conditions, this strategy produces a schedule with the maximum possible number of meetings. Greedy algorithms build solutions step by repeatedly making the best local choice available without going back to change earlier decisions. They rely on two key ideas. Any good partial solution can be extended into a full solution, and locally optimal choices will lead to a globally optimal result. For example, a delivery company loading a truck with limited space might always add the package with the highest value per unit of weight that still fits. This approach assumes that each such choice moves the solution toward the best overall outcome. Greedy algorithms build a solution by repeatedly making the best available choice at each step without revisiting earlier decisions. They work correctly when any globally optimal solution can be formed from these locally optimal choices. So the first step of an optimal solution matches the greedy choice, and the remaining steps can be solved in the same way. This structure lets us use inductive reasoning. If the first greedy step is correct and the problem keeps the same form, then applying the greedy rule again and again leads to an overall optimal solution. When these conditions hold, the greedy method is both efficient and guaranteed to find the best answer. Python code, building optimal solutions. We want to demonstrate how a greedy strategy can build an optimal meeting schedule by always choosing the meeting that finishes earliest. At each step, once we select the earliest finishing meeting that does not conflict with those already chosen, that choice is fixed and never needs to be changed. By repeating this process, each local earliest finishing decision becomes a permanent part of the schedule. Taken together, these locally optimal choices accumulate into a globally optimal meeting schedule that fits the maximum number of non-overlapping meetings. The comment about installing Matplotlib, Seaborn, NumPy, and Pandas explains that these libraries are commonly used for data visualization and data manipulation, but they are not needed for this particular example. It serves as a reminder for users who may want to expand the code later with plotting or data analysis features. For the current goal of creating an optimal meeting schedule, these extra libraries are optional and not required. We represent each meeting as a pair of numbers, the start time and the finish time, both measured in hours. Collecting these pairs into a list makes it easy to compare when meetings begin and end. This structure lets us sort the meetings by their finish times and then select among them efficiently. That sorting step is essential for applying a greedy algorithm to build an optimal meeting schedule. To build an efficient meeting schedule, we first sort all meetings by their finishing times. This ordering supports a greedy strategy, where we always consider the meeting that ends the earliest before any others. A sorting tool uses a small helper rule that looks at each meeting's finish time and arranges the list based on that value. Once the meetings are sorted this way, we are set up to choose an optimal set of meetings by repeatedly picking the earliest finishing one that fits. We begin by creating an empty list that will store the meetings chosen for our optimal schedule. We also set a tracking value, called the current finish time, to 0. This value records when the last selected meeting ends. Each time we consider a new meeting, we compare its start time to this current finish time to make sure it does not overlap with any meeting already in the schedule. We process the sorted list of meetings one by one, looking at each meeting's start and finish times. For each meeting, we check whether its start time is at or after the finish time of the last meeting we accepted. If it is, we add this meeting to our schedule and update the current finish time to this meeting's finish time. By always choosing the next meeting that finishes earliest without overlapping, we gradually build an optimal schedule. We begin by printing all the candidate meetings with their start and finish times so we can see the full set of options. Then, we display the same meetings sorted by their finishing times. This ordering is essential for the greedy scheduling algorithm because it lets us always pick the meeting that ends earliest. By doing so, we maximize the number of meetings we can attend without overlaps. Here we present the final schedule produced by the greedy algorithm. The meetings were chosen in order of earliest finishing time, so each step made the best possible local choice that could not be reversed. Viewing the completed schedule shows how these local decisions combine into a globally optimal solution. This demonstrates the effectiveness of the greedy strategy for this scheduling problem. This line prints a message explaining how the schedule was built. It states that each meeting was chosen because it finished earlier than any other available option at that time. Once a meeting is chosen, it is permanently added to the schedule. This shows how making the best local choice at each step leads to the overall optimal solution. This script shows how a greedy algorithm can build an optimal schedule of non-overlapping meetings. It begins with a list of meetings defined by their start and finish times, then sorts them by when they finish. The algorithm goes through this sorted list and selects a meeting only if it starts at or after the finish time of the last chosen meeting. By always picking the earliest finishing meeting that fits, it produces a globally optimal schedule. When run, the script displays all candidate meetings, the final optimal schedule, and a short explanation of how each local choice leads to the best overall result. Local versus global choices. In this strategy, the main issue is the difference between local and global choices. A local choice picks what looks best right now, using a simple rule, while a global objective focuses on the overall goal, such as maximizing profit or minimizing cost. Greedy algorithms rely on the idea that always taking the best local option will produce a globally optimal solution. However, this does not always work because the best immediate action can sometimes prevent the best overall outcome. Therefore, it is important to understand when local and global goals actually line up. Imagine planning a road trip where you always choose the road that looks shortest at each intersection without thinking about future traffic or detours. This kind of greedy choice can seem efficient at first, but may lead to a longer, less effective route overall. The same idea applies to personal finance, where always picking the lowest immediate cost can block better long-term investments. These examples show that strategies focused only on immediate gains are appealing, but do not always produce the best overall outcome. Their success depends on the underlying structure of the problem, just as it does in algorithm design. In algorithm design, a central question is whether making the best choice at each step will lead to the best overall solution. When local and global goals align, as in some scheduling and routing problems, a greedy strategy that always takes the locally optimal option can be both simple and effective. However, many problems require short-term sacrifices or coordinated decisions, so local choices alone are not enough. The key challenge is to recognize when local and global optimality match, allowing a straightforward, step-by-step method to achieve the best overall result. Classic greedy algorithms. Interval scheduling strategy. The interval scheduling problem asks you to choose as many non-overlapping activities as possible given their start and finish times. You can think of it as scheduling meetings in one room or shows on a single TV tuner, where only one activity can run at a time. A simple greedy strategy works optimally here. Always select the activity that finishes earliest among those that are compatible with the activities you have already chosen. By repeatedly making this locally best choice, you end up with an overall schedule that contains the maximum number of activities. To use the greedy interval scheduling algorithm, first sort all activities by their finishing times. Then scan through them in that order while remembering when the last chosen activity ended. For each new activity, if its start time is at or after this remembered finish time, select it and update the finish time to this activity's end. If it starts earlier and would overlap, skip it. In Python, This means sorting the list of time intervals and using a simple loop with a condition to build a schedule of non-overlapping activities. The greedy interval scheduling approach is a practical way to maximize how many tasks you complete when resources are limited. It is used in settings like hospitals scheduling patients on machines and ride-sharing platforms planning driver trips. In Python, you can adapt this method to many domains by changing how you define the time intervals, while keeping the core idea the same. Sort tasks by their finish time and repeatedly choose the next one that does not overlap with what you have already selected. This simple pattern makes it a powerful template for building greedy scheduling solutions. Python code interval scheduling strategy. We can demonstrate the greedy interval scheduling strategy in Python using simple lists and loops to represent activities with start and finish times. By first sorting the activities by their finishing times, we can then scan through the list and repeatedly select the next activity that starts after the last chosen one finishes. This greedy choice ensures we pick the maximum number of non-overlapping activities. Finally, we print the selected activities to show which meetings can be scheduled in a single shared conference room without conflicts. This comment explains that you do not need to run any pip install commands because the script only uses Python's built-in libraries. In other words, the code is self-contained and has no external dependencies. As a result, it is easy to run and does not require any extra setup or package installation. We represent our schedule as a list of activities where each activity is stored as a tuple containing the meeting name, start time, and finish time. This structure makes it easy to manage and process the schedule. For example, we include meeting A from 9 to 11, meeting B from 10 to 12, meeting C from 11 to 13, meeting D from 13 to 14, and meeting E from 12 to 16. Organizing the data this way is especially useful when we later sort and select activities based on their timing constraints. The code sorts a list of activities by their finish times using Python's built-in sorting function with a small helper that extracts each activity's finish time. This ensures the activities are ordered from earliest to latest finish. Sorting by finish time is essential for the greedy interval scheduling strategy because it allows the algorithm to choose the largest possible set of activities that do not overlap. We begin by creating an empty list to store the activities chosen by our greedy strategy, which will eventually hold all the non-overlapping activities that meet our criteria. We also set a variable called the current finish time to 0. This value records when the last selected activity ends, so that each new activity we consider must start after this time. In this way, we systematically build a set of compatible activities that do not overlap. We process the activities in sorted order, and for each one, check whether its start time is at or after the current finish time. If it is, we select that activity and update the current finish time to its finish time. By repeating this for all activities, we always choose the next compatible activity as early as possible. This greedy strategy produces the maximum number of non-overlapping activities. The code first prints a message explaining that it will show all activities along with their names, start times, and finish times, so the user knows what data is being processed. It then prints the full list of activities as tuples containing this information. This lets the user see the original set of activities before any selection is made. Later, they can compare this initial list with the final set of non-overlapping activities chosen by the script. We now display the final set of selected activities that do not overlap in time. These activities were chosen using a greedy strategy, which picks compatible meetings step by step. The printed list shows exactly which meetings can be scheduled without conflicts. This result represents a valid schedule for using a single conference room. This script shows how a greedy interval scheduling strategy can select the largest possible set of non-overlapping meetings. It starts with a list of meetings, each defined by a start time and a finish time, and sorts them by when they finish. It then goes through the sorted list and picks each meeting that begins at or after the finish time of the last chosen meeting, ensuring there is no overlap. The final output is a subset of meetings that can all be held in a single conference room without conflicts, demonstrating the effectiveness of the greedy approach. Extended activity selection. The activity selection problem builds on interval scheduling by adding more complex constraints and goals, such as managing multiple conference rooms or assigning several technicians. The aim is still to maximize the number of completed activities while respecting limited resources. The key strategy is to make locally optimal choices, like always picking the earliest finishing activity that fits into a resource's schedule, then updating which activities remain feasible. The main challenge is to turn this idea into an efficient algorithm that can handle multiple resources in Python while staying simple and effective. In an extended activity selection algorithm, you first sort all activities by a key, such as their finishing times. As you scan through the sorted list, you track the current state of each resource, usually by its latest finishing time. For each new activity, you look for a resource whose current end time is not later than the activity's start time. If such a resource exists, you assign the activity to it and update that resource's finishing time. If not, you skip the activity. In Python, this logic is implemented with loops, condition checks, and suitable data structures like lists or priority queues to always choose the next feasible activity. Extended activity selection is important for real-world scheduling problems, such as assigning surgeries to operating rooms or deliveries to trucks. By modeling each task with a start and finish time, and each resource with its availability, you can implement and test scheduling strategies in Python. You can try different greedy rules, like giving tasks to the resource that becomes free first, or preferring shorter tasks when there is a tie. Running these strategies on sample data shows how well the greedy approach works and how it responds when resources or task durations change. This practical experimentation deepens your understanding of the algorithm and how to keep your code efficient and flexible. Python code, extended activity selection. We will extend the activity selection problem to handle multiple conference rooms using a greedy strategy. By sorting all talks by their finishing times, we can efficiently assign each talk to the first room that becomes available. This approach ensures that talks are scheduled without overlap in any room while making good use of the available space. Finally, we will print the resulting schedule, clearly indicating which talk is assigned to each conference room. This comment explains that pip install commands are not needed because the script uses only Python's standard libraries. All required features come from built-in modules, so no extra packages have to be installed. As a result, the script is self-contained and can run immediately. The comment simply clarifies that no additional setup is required. We represent each talk as a tuple with 3 parts: its start time, its finish time, and its name. Using start and finish times in hours makes it easy to compare and sort the talks by when they occur. Each tuple corresponds to one distinct talk, such as a session that runs from 9 to 10. This structured format is important because it lets us efficiently organize and schedule the talks into available conference rooms later in the program. We assume there are 2 available conference rooms for scheduling talks. This means we have 2 separate spaces where activities can take place. This number determines how many room schedules we must track and is used to check whether a room is free for each talk. To schedule activities efficiently, we first sort them by their finishing times, using a function that looks at the second value in each activity pair, which represents when it ends. Sorting by finish time lets us apply a greedy strategy. We always consider the activity that finishes earliest before looking at later ones. This method helps us choose the maximum number of activities that do not overlap, making the best use of the available rooms. We begin by creating a list that tracks when each conference room is next available. This list is filled with zeros, 1 for each room, to show that all rooms are free at the start of the day. Using a single pass over the number of rooms, we set every room's availability time to 0. This means every room is ready to host activities immediately from the early morning. We set up a list to represent the schedule for each conference room, where each room has its own sublist to store its assigned talks. A list comprehension is used to quickly create an empty sublist for every available room. With this structure in place, we can easily add each talk to the correct room's sublist as we build the overall schedule. We process the list of activities one by one in order of their finish times, and for each activity, we look at its start time, finish time, and name. This step-by-step scan lets us decide which conference room each activity can use without overlapping with others already scheduled. By always considering the earliest finishing activities first, we follow a greedy strategy that helps minimize idle time and make the best use of all available rooms. The code is selecting a room for an activity so that it does not overlap with other scheduled activities. It begins by marking that no room has been chosen yet, then loops through all available rooms. For each room, it checks whether the activity start time is later than or equal to the time when that room becomes free. If this condition is met, the activity can be placed in that room without conflict, so the code records that room's index and stops searching. When a suitable room is found, the program assigns the current activity to that room by adding its start time, finish time, and name to that room's schedule. This action reserves the room for that specific time slot. Afterward, the room's next available time is updated to the activity's finish time. This prevents any later activities from being scheduled in that room during an overlapping period. We now present the final schedule for the activity selection process, which summarizes how the talks are assigned to the available conference rooms. This announcement acts as a header for the detailed distribution of talks that follows. It reflects the outcome of applying a greedy algorithm designed to allocate activities efficiently. The key result is a non-overlapping arrangement of talks that makes effective use of the conference rooms. We go through each room in order, using its index to access the list of scheduled talks. For every room, we announce the room number in a human-friendly way by starting the count at 1. Then, we list each talk assigned to that room, stating its name along with its start and finish times to show the duration. If a room has no talks scheduled, we clearly say that no talks are assigned there today. This process gives a complete and easy-to-read overview of the schedule for all rooms. This script shows a greedy method for scheduling talks in multiple conference rooms. It first sorts all talks by their finishing times. Then, with 2 rooms available, assigns each talk to the earliest free room so that no talks overlap in the same room. The outcome is a schedule where each room has an ordered list of talks with their start and end times. When you run the script, it prints this schedule, illustrating how the rooms are used efficiently without conflicts. Greedy coin change. The coin change problem can be solved using a greedy strategy that aims to use the fewest coins possible. You first sort the coin denominations from largest to smallest, then repeatedly choose as many of the largest coin as you can without going over the remaining amount. After that, you move to the next smaller coin and continue this process until the total amount is reached. For example, to make 37 units using coins of 25, 10, 5, and 1. This method selects 125, 110, and 2 ones for a total of 4 coins. This illustrates how the greedy approach works in a simple and efficient way. In Python, the greedy coin change strategy works by keeping track of the remaining amount and how many coins of each type are used. You first sort the coin denominations from largest to smallest, then for each one, use integer division to find how many of that coin fit into the remaining amount and subtract their total value. You repeat this for all denominations until the remaining amount is 0 or you run out of coin types. This approach is efficient because there are usually only a few coin denominations, and it reflects how cashiers and vending machines typically make change. When using the greedy algorithm for coin change, be aware that it does not always give the fewest coins for every possible set of denominations. In some systems, always picking the largest coin first can actually lead to using more coins than necessary. Its reliability depends on the specific properties of the coin set, such as those found in many standard currencies. You should test your implementation with known counterexamples to check whether the greedy method is appropriate. This is especially important for non-standard currencies, like loyalty points or game tokens, where blindly applying the greedy approach can produce inefficient results. Python code. Greedy coin change. This example demonstrates the greedy coin change algorithm using common United States coins. The method always picks the largest possible coin first, subtracts its value from the remaining amount, then repeats with the next largest coin until the change is made. By walking through the choices step by step, you can see how each largest coin selection reduces the remaining amount. Finally, you compare the total number of coins used by this greedy approach with the total coins needed for the same change amount to evaluate how effective the greedy strategy is. This comment explains that the script uses only Python's built-in features and does not depend on any external libraries. As a result, users can run it without installing extra packages. This makes the script easier to use and more accessible since it works with a standard Python installation. To compute greedy coin change for a given amount in cents, we define a function that first sorts the coin denominations from largest to smallest, so we always try to use the biggest coin available. We then create a dictionary to record how many coins of each denomination are used, starting all counts at 0. Finally, we set a variable for the remaining amount to be changed, initially equal to the full input amount, and this will be reduced as we choose coins according to the greedy strategy. In this greedy coin change approach, we go through the coin denominations in sorted order from largest to smallest. For each coin, we use integer division to find how many of that coin fit into the remaining amount. If we use at least one, we record this count, then reduce the remaining amount by the remainder from that division. We repeat this for each denomination, always trying to use as many large coins as possible before moving to smaller ones. This function finishes by returning two results, a dictionary and a remaining amount. The dictionary records how many coins of each denomination were used to make the change. The remaining amount shows what part of the original value could not be converted into coins. Ideally, this remaining amount is 0, meaning the entire value was successfully broken down into coins using the greedy method. We define common United States coin denominations as 25, 10, 5, and 1 cent, which are the values used to make change. As an example, we choose an amount of 37 cents as the total change needed. We then apply a greedy coin change function that takes this amount and the list of denominations and computes how many of each coin are required to reach the total using the fewest coins. The function returns the counts of each coin type and any remaining amount, which should be 0 if the coins can exactly make up the desired total. We begin by printing a short header that explains we are computing the greedy coin change for 37 cents using standard United States coins. Then we go through each coin type in order from the largest value to the smallest, matching the greedy strategy. For every coin type, we display the coin's denomination and how many of those coins are used. This produces a clear breakdown of how the total amount is formed using as many large coins as possible before moving to smaller ones. To finish the coin change process, we first add up all the counts in the dictionary of coin types to find the total number of coins used. We then print this total, so it is clear how many coins were needed to make the change. After that, we print the leftover amount, which should be 0 if the coin denominations can exactly represent the original amount. This final value shows whether the greedy algorithm successfully converted the entire amount into coins without any remainder. This script illustrates a greedy algorithm for making change with standard US coins. It computes change for 37 cents by always choosing the largest coin value available first, using denominations ordered from largest to smallest. The program reports how many of each coin are used and verifies that no amount is left over, meaning the change is exact. For 37 cents, it selects 1 quarter, 1 dime, and 2 pennies, for a total of 4 coins, showing that the greedy method is efficient for this coin system. Testing greedy correctness. Building greedy counterexamples. When you suspect a greedy algorithm might fail, a powerful strategy is to design counterexamples. Instead of guessing randomly, you carefully construct inputs where the algorithm's local, step-by-step choices do not produce the best overall solution. To do this, analyze what the algorithm prioritizes, such as the largest item or the earliest interval, and then imagine cases where following that rule leads to a bad outcome. This process exposes edge cases that reveal the gap between local reasoning and global optimality. To build a counterexample for a greedy algorithm, start from a known optimal solution and then adjust it so the greedy rule makes a bad choice. For a scheduling problem, you might design an optimal schedule using several medium-length tasks that all fit before a deadline. Then introduce one task that looks especially attractive to the greedy rule, perhaps because it has a high reward or an earlier start time. But that task prevents other tasks from fitting. By carefully tweaking start times, durations, or rewards, you can create a situation where the greedy choice blocks more total tasks from being completed. This shows how a seemingly appealing local decision can lead away from the global optimum. As you gain experience, you can improve at designing counterexamples by targeting weak spots such as tie situations, boundary cases, and interactions between choices. For greedy algorithms, test what happens when two options look equally good and see if different ways of breaking ties lead to success or failure. Also examine extreme input sizes and choices that seem good now but block better options later, like a cheaper route that prevents a more profitable one. By probing these delicate cases, you both test the algorithm's correctness and reveal where local decisions may conflict with the overall goal. Python code. Building greedy counterexamples. Show how a greedy algorithm for coin change can fail by giving a simple counterexample where it does not find the best solution. For the same set of coin denominations and the same target amount, compare the greedy choice, which always takes the largest possible coin first, with the true optimal solution that uses fewer coins. Emphasize the contrast between these two outcomes so students clearly see that greedy choices can be locally appealing but globally suboptimal. Finally, guide students to notice the pattern in such examples so they can deliberately construct their own counterexamples to test greedy algorithms. The line with the pip install command is just a humorous placeholder comment, not real code. It indicates that the script does not need any extra Python packages to run. Instead, it uses only built-in Python features. Its purpose is to remind you that the code is self-contained and has no external dependencies. To solve the coin change problem with a greedy method, we define a function that takes a total amount in cents and a list of coin denominations. It starts with an empty result list and sets the remaining amount to the total. The coin values are sorted from largest to smallest, so higher denominations are used first. For each coin, The function computes how many of that coin fit into the remaining amount using integer division, subtracts their total value from the remaining amount, and records the coin value with its count. In the end, it returns the list of coin counts along with any leftover amount that cannot be represented with the given coins. This function uses a brute force method to find the best way to make change for a given amount. It tries all possible combinations of the available coin types by looping through different counts of each coin. For each combination, it checks whether the total value matches the target amount, and if so, counts how many coins are used. It keeps track of the solution that uses the fewest coins and updates this best solution whenever a better one is found. In the end, it returns the combination of coins that makes the target amount with the smallest number of coins. Consider a set of coins worth 10, 7, and 1 cent, and a target amount of 14 cents. This example is chosen because it creates a situation where a greedy algorithm, which always picks the largest coin first, does not produce the best solution. By using this specific combination of coin values and target amount, we can clearly show that the greedy approach can fail, and that more advanced methods may be needed to find the optimal result. To begin solving the coin change problem, we first run the greedy algorithm, which always tries to use the largest coin denominations available to reach the target amount. We give this procedure the total amount and the list of coin values, and it returns the coins it chose along with any leftover amount that could not be matched exactly. This initial greedy result is important because it provides a baseline we can compare with the optimal solution, allowing us to see where the greedy method may fail to find the best possible combination of coins. We use a brute force method to find the optimal way to make change. This method calls a function that checks every possible combination of the available coin denominations to reach the target amount. By exploring all options, it identifies the combination that uses the fewest coins. Although this approach can be more computationally expensive than a greedy method, it guarantees the minimal number of coins needed. The count total coins function calculates how many coins are used in a given solution. It receives a list where each entry describes a coin type and how many of that coin are used. The function goes through this list, takes the coin counts from each entry, and adds them together. It then returns this sum as the total number of coins. This helper is useful for comparing different coin change solutions based on how many coins they require. The code first prints a brief description of the coin system and the target amount of money. It shows which coin denominations are available, expressed in cents, and the total amount in cents we want to make. This initial output establishes the problem setup and provides the context needed to later compare the greedy solution with the optimal solution for making change. We display the results of the greedy solution by showing which coins it selects and any remaining amount it fails to match. This output demonstrates how the greedy method behaves for a specific coin system and target value. By examining the chosen coins and any leftover amount, we can see where the greedy approach may be inefficient or unable to reach the exact target due to its inherent limitations. We begin by showing the details of the optimal solution, including which coins are used, found earlier using a brute force method. Then, we call a helper function that adds up the counts of each coin type in this solution to get the total number of coins. This tells us exactly how many coins the optimal strategy needs, so we can directly compare it with the number of coins used by the greedy approach. We compare how many coins the greedy algorithm uses with how many the optimal solution uses. To do this, we first compute the total number of coins in the greedy solution by summing the counts of each coin type. We then state that the greedy method uses this total number of coins. Finally, we point out that the optimal solution uses fewer coins, showing that the greedy approach fails to find the best answer in this example. This example shows how a greedy algorithm can fail to find the best solution in a coin change problem. With coin values of 10, 7, and 1 cent, and a target of 14 cents, the greedy strategy always picks the largest coin first. It chooses one 10-cent coin and then 4 1-cent coins, reaching 14 cents, but using 5 coins. A brute force search finds a better solution, 2 7-cent coins, using only 2 coins in total. By printing both results, the script clearly illustrates that the greedy method is suboptimal in this case. Greedy versus brute force. To judge whether a greedy strategy is reliable, it helps to compare it conceptually with a brute force approach. Brute force checks all possible solutions and always finds the optimal one, so it serves as a standard for correctness. A greedy algorithm instead makes the best choice it can at each step based only on the current situation. By asking whether the greedy method always matches the brute force result, or whether brute force can sometimes do better, you can assess how correct the greedy approach really is, even if you never actually run the exhaustive search. Brute force methods are mainly useful as conceptual or experimental tools rather than for real production use. For small problem sizes, you can list all possible solutions, evaluate them, and identify the true optimum. You then run your greedy algorithm on the same test cases and compare its results to the brute force optimum. If the greedy answers consistently match the brute force solutions, that is evidence the greedy rule may be correct. This strategy is especially helpful in teaching and in early stages of algorithm design to build intuition about how the problem behaves. To see why a greedy algorithm can be correct, compare it to a brute force method that explores every possible solution. You can imagine all solutions as a large tree, where brute force checks every branch, but the greedy method quickly cuts off many branches by making local choices. Each greedy choice must be justified by showing that any other choice could be rearranged to match the greedy one without making the result worse. This type of reasoning, called an exchange argument, shows that the greedy solution is as good as the best solution brute force would find. Using this comparison helps confirm that a faster, streamlined greedy approach is still reliable for tasks like planning routes or allocating resources. Python code, greedy versus brute force. This example compares greedy and brute force approaches to the coin change problem using a simple amount. The brute force method explores all combinations to find the truly optimal solution, while the greedy method quickly picks the largest possible coin at each step as an approximation. You will see cases where the greedy choice happens to match the optimal brute force result, and other cases where it fails to find the best solution. The script relies only on the Python standard library, so no additional installation commands are needed. We begin by defining the coin denominations we will use based on standard United States currency. These are quarters worth 25 cents, dimes worth 10 cents, nickels worth 5 cents, and pennies worth 1 cent. This set of values forms the basis for our coin change calculations and will be used consistently in both the greedy algorithm and the brute force approach that follow. To compute the number of coins needed using a greedy method, we first sort the coin denominations from largest to smallest, so we always try to use the biggest coin available. We keep track of the remaining amount to make change for and a running total of coins used. For each coin value, we calculate how many of those coins fit into the remaining amount. Add that number to our total and subtract their combined value from the remaining amount. After processing all denominations, the function returns the total number of coins used by this greedy approach for the given amount. We use the product function from the itertools module to generate the Cartesian product of the coin counts for each denomination. This means we systematically list every possible combination of coins that could make up a given amount. By checking each combination, we perform a brute force search over all options. This exhaustive approach guarantees that we find the way to make change using the minimum number of coins. The function tries to find the smallest number of coins that add up exactly to a given amount. It starts by assuming a worst case where the amount is made entirely of pennies and sets an initial best value that is larger than any real solution. It then systematically explores all possible combinations of coin counts for each denomination and computes the total value for each combination. Whenever a combination matches the target amount, it counts how many coins are used and updates the best value if this count is smaller. In the end, it returns the smallest coin count found or returns nothing if no exact combination is possible within the maximum limit. This script compares two ways to solve the coin change problem, a greedy method and a brute force method. Both aim to find the minimum number of coins needed to make a given amount. With standard US coins and an amount of 63 cents, both methods give the same optimal result, so the greedy strategy works well. But with a tricky set of coins, such as 10, 9, and 1 cent pieces used to make 18 cents, the greedy method fails while brute force still finds the best solution. This shows that although the greedy approach can be efficient, it does not always produce the optimal answer for every set of coin denominations. Spotting greedy pitfalls. When using a greedy strategy, you must watch for situations where choices depend heavily on future decisions. Greedy algorithms assume each step can be optimized on its own, but this fails when the best immediate option blocks better combinations later. For example, always driving the maximum distance on a road trip might seem efficient, but can lead to worse overall stops than taking shorter daily drives. In general, if early decisions strongly restrict what you can do next, a purely greedy approach that only looks at the next step is likely to be unreliable. Greedy methods work best when the total objective is simply the sum of independent parts, so that each local choice does not affect the others. When the objective involves complex trade-offs, such as ratios or nonlinear penalties, a choice that looks best locally can harm the overall result. In these cases, focusing only on the single best option, like always picking the most qualified candidate, can lead to a worse overall outcome, such as an unbalanced team. Whenever multiple criteria must be balanced, or each decision depends on previous ones, a simple greedy strategy is likely to miss the bigger picture. Greedy algorithms can fail in situations where past decisions can be revised, such as reallocating resources or backtracking. Because they lock in each choice based only on immediate benefit, they ignore the possibility of better options that appear later. In areas like portfolio management or project scheduling, where conditions change and flexibility matters, this can lead to worse long-term results. For problems that require adaptability or negotiation, you should carefully assess whether a greedy strategy can truly provide the best overall solution. In this lecture, you learn to describe the greedy algorithm design paradigm and its key assumptions, implement classic greedy algorithms in Python for problems such as interval scheduling or coin change, and evaluate whether a greedy approach is likely to be correct for a given problem. In the next lecture, Lecture B, we will go over greedy in Python. Thank you for your attention. See you all in the next lecture.